and welcome back to Physics in Action. I am your host, Miss Nielsen, and today we are moving beyond motion. We know that objects can travel at a constant velocity. We know that objects can accelerate by speeding up or slowing down or by turning. The question is, why do objects move the way they move? Why can things do the things that they do? And that question, the answer to that question, we will discover today. That's right, folks. Today we are reporting on the phenomenon known as forces. First, we're going to head over to the lab and we are going to talk about the 5 fabulous forces in physics that we will be studying. Then we're going to head over to my classroom and I will teach you all about the father of forces himself, Isaac Newton, and his 3 laws of motion. 3 laws of motion. As usual, you are going to want to take notes on today's report. Let's head over to the lab and discover those 5 fabulous forces. Before we even talk about the fabulous 5 forces, we need to actually discover what is a force. Simply put, a force is just a push or a pull on an object in any direction. Doesn't matter which direction it is, but the fact that a force considers the direction tells us that force is a vector. Yeah. So if I take this textbook and I push it, I exert a force on it. If I pull it, I also exert a force on it in any direction. If I pick it up, I push it up, I'm exerting a force. If I push it down, I'm exerting a force on it. We use that word exert a lot when we talk about forces. Forces is something that you do to an object. You exert a force on an object. So the 5 fabulous forces in physics that we care about, we're going to break these down a little bit more here in just a second. But we have the force of gravity. We have the normal force. I guess the table must be pushing up on it or something. We have the force of friction. And we have the force of tension. And finally, we have the applied force. 1, 2, 3, push! 1, 2, 3, push! These are the fabulous 5 forces in physics. So now it's time to go over some really important vocabulary for this new unit that we're in, starting with, of course, the word force. So a force is, just like we said, it's a push or a pull on an object in any direction. The fact that force considers the direction means that force is a vector. So a force must have a magnitude and a direction. You could push something to the left, you could pull something backwards. Force has a direction. Also, we want to think about the units of force. The unit for force is newtons, named after Isaac Newton. We abbreviate it with a capital N, and we will be talking about Isaac Newton later today, but a newton isn't like a standard unit of measurement. It's actually made up of other units. So 1 newton is the same thing as 1 kilogram times meters per second squared. So rather than saying you're pushing something with 40 kilogram meter per second squared, that's a lot to say. It's easier just to say you're pushing something with 40 newtons of force. So it's just a derived unit from kilograms and meters per second squared. So before we talked about the 5 fabulous forces in physics, which are the force of gravity, number 1, number 2, the normal force, number 3, the force of friction, number 4, the force of tension, and number 5, the applied force. So we're going to break down each one of these individually, what they mean, where we see them, why we care, and some examples. So starting with the force of gravity, The force of gravity is really special to us. We abbreviate it with Fg, F with a little g for gravity. The force of gravity on an object is actually the weight of an object, and it's because of the Earth's pull. The Earth's gravitational pull on an object causes an object to have weight. So the force of gravity is the same thing as the weight of an object, how heavy something is, how heavy something feels. And we can actually calculate the force of gravity on Earth, on any object. We know that it's the weight, but we can actually calculate what that is. So Fg, or the force of gravity, we know is equal to the weight, they're the same thing, which is equal to m, the mass of an object, times this special quantity g. So we want to really remember this equation. We know W is weight, Fg is the force of gravity, m, I said, was the mass of an object, and g is a really special quantity. It's the acceleration due to gravity. So if you take a pen and you drop it, it's going to fall down to the ground. It's going to accelerate because of gravity, it's going to accelerate at a rate of 9.81 meters per second squared downward. So this is how we calculate the force of gravity on any mass, on any object on Earth. But now we want to talk about the difference between mass and weight really quickly. So we know weight is the force of gravity on an object, but the mass we measure in kilograms, which we saw over there in that unit for newtons. The mass of an object is just the amount of matter in an object. So how much stuff is in something is its mass, which stays the same no matter where you're located in the universe. Also, something really important to note about the force of gravity is that it always points straight down because the Earth pulls straight down on those objects. So now we're going to take a look at the difference between mass and weight. Before we start talking about Newton's laws, it's really important that we make the distinction between mass and weight because they are not the same thing. Mass is measured in kilograms, and it is the amount of matter in an object. And that amount of matter stays the same no matter where you're located in the entire universe. So what I've got here are some masses. I've got different size masses here. The biggest one, I'm not sure if you can see that, is 1 kilogram. That's this guy. So this is a 1 kilogram mass. The amount of mass in an object is really just related to how much space it takes up and how dense it is. So this is pretty dense, takes up this much space, which means it's a kilogram of mass. And if I took this kilogram to the moon, it would still be 1 kilogram. But weight, the weight of an object is actually the force of gravity that acts on an object, which can change depending on where you are in the universe. So on Earth, when we measure our weight, we step onto a scale. But if we took that scale to the moon and we stepped on it there, we would weigh different than we do here because gravity is different wherever you're located in the universe. In terms of on Earth, what I'm going to do to measure the weight of this mass is I have a little force reader here. It's going to read the force that's acting on my little hook. I'm going to hook my mass, make sure it's zeroed first. Let's zero it. I'm going to hook my mass here on my force reader, and it is telling me that my mass is, in terms of its weight, is about around 10 newtons. We know that newtons is the unit of force, which is also the unit of the force of gravity, which is the unit for weight. So my 1 kilogram mass weighs approximately 10 newtons, right around 10 newtons. That is the difference between mass and weight, and we always have to remember that mass is measured in kilograms, but weight, or the force of gravity on an object, is measured in newtons. Next up is the normal force. The normal force doesn't refer to like normal versus unusual. The normal force is abbreviated as F with a little n, and the normal force is kind of really special. It's actually the force that is exerted on an object by a surface. So I'll give you an example here. Let's say you have a table and you put a book on that table. We know that the force of gravity is going to pull down on that book because it has mass it must have weight on the earth, okay? Earth is going to pull down on it, but what is keeping it supported on the table? There must be some force that the table is exerting on the book that pushes it up, that supports it. So we could call that the force from the table. But instead of calling it the force from the table is a surface, which means that that force is the normal force. That table is our surface that's supporting the book, that's pushing up on the book. So that table is providing that support force, which is the normal force. I like to call the normal force the support force sometimes. It's also important to note that the normal force always pushes perpendicular to the surface. So we had a table which was flat, horizontal, and that normal force pointed straight up, which means that's perpendicular. So our normal force is always going to point perpendicular away from the surface. It's going to push away. And that's the normal force, so nothing too special there. Next up is the force of friction. The force of friction we like to abbreviate as FF, force of friction, FF. The force of friction is also a really unique force, and we really like to talk about it in physics. It's the force between two surfaces that resists the motion of an object. So two surfaces, you could think of your hands, your left hand and your right hand are two surfaces. If you rub them together, they're going to resist that motion and you feel the heat, right? You feel heat between your hands because of friction. Actually, the harder you push, the harder it is to move your hands together. And that actually relates to how we calculate the force of friction. The force of friction is related to the normal force, which we just talked about, the surface force. And it's related by this little weird M that we have. So we know that FF stands for the force of friction. Fn is the normal force. And the way that the two are related is by this mu, it's a Greek letter M. It stands for the coefficient of friction, which is unique to the two surfaces that are in contact. So let's say you're ice skating, that would be the ice and then the metal on your ice skates. If you're walking on a sidewalk, it's going to be the concrete of the sidewalk and the rubber on your shoes. So depending on that coefficient of friction depends on how much friction there is between the two surfaces. But friction is always going to point opposite the direction of motion. So if you're pushing something to the right, friction is going to pull or push to the left. It's always going to be opposite of what you're trying to move, in which direction you're trying to move. And that's the force of friction. Next up is the force of tension. Sometimes we just call it tension instead of the force of tension, but tension can be abbreviated with FT. And the force of tension is just the force that's in or along a rope or a string or anything that you're kind of like pulling on. So there's tension in your muscles, there's tension in your tendons, there's tension in all different types of things, but usually we just consider a rope or a string. So let's say you're in the airport, you're lugging a suitcase, you're pulling on that suitcase, you're running. There's going to be tension in the handle of your suitcase because you're pulling on it. Even though it's not a rope or a string, it is kind of what you're pulling on, so there's some tension in there. And since you're pulling kind of up and to the right on it, that's the way that the tension will point, right? So the tension is always going to point in the direction of the string or the rope or whatever you're pulling on. That's kind of where tension comes from. And tension is just that. It's pretty simple. Our last force is the applied force. So this is a pretty simple force here. We just call it FA, and it's kind of just a catch-all. So anytime that you are pushing or pulling, just like in general on something, we usually call that an applied force. So it's like when you are directly acting on an object, you are applying that force. It's an applied force. So let's say you're pushing a cart. You're pushing a cart on a flat surface, you're pushing it to the right, you yourself are applying a force on the cart. So your applied force would be pushing to the left, or to the right, sorry. To the right because you're moving to the right. So the applied force is just a general push or pull on an object. So when we think of the word force, it's kind of like applied force. It's just when you're doing that. And those are the 5 fabulous forces in physics. Next up, it's time to talk about Newton's laws. So Newton is Isaac Newton, who's this guy right here. He is the kind of father of forces. He's the guy who sat underneath the apple tree and watched it fall one day and thought too much about the universe and came up with these laws. He also invented calculus. But Newton's laws refer to specifically the laws of motion and relating to forces. So there are 3 laws of motion. The first law is one that you've probably heard before. Objects at rest will stay at rest. Objects in motion will stay in motion. Unless it's acted on by an unbalanced force. To summarize, it's an object at rest will stay at rest, and an object in motion will stay in motion unless acted on by an unbalanced force. This law is often called the law of inertia. Inertia is a really weird word, but we're going to talk about what that means here in a second. But this law, you've probably heard it before. It's the first law of motion. It's super important to us. So what exactly is inertia? Well, an object's inertia is very closely related to the object's mass. And as we just said, mass is the amount of matter in an object. But inertia specifically is an object's tendency to resist a change in motion. So right here, I have a nice Jenga stack. And what I'm going to do is I'm going to remove the 2 bottom pieces of my Jenga stack so that it's balancing on just one. And what am I going to do with this? Well, I'm going to take advantage of this object's, my Jenga stack. I'm going to take advantage of its inertia. So right now my Jenga stack is at rest and it wants to maintain that state of motion, no motion. According to Newton's first law, an object at rest will stay at rest unless acted on by an unbalanced force. So I could be the unbalanced force and I could just push this tower over and it would fall. But if I take advantage of this object's inertia, I can actually remove that bottom piece very easily. And what I'm going to do is I'm going to take my meter stick and just kick it out as fast as I can. And what's going to happen is the object, its inertia, is going to want to resist that change in motion and it's not going to fall over. Ready? 3, 2, 1. So you see that some of the blocks did in fact slide around, but overall, the tower maintained its state of motion. No motion. And that's Newton's first law. The second law of motion is a little bit different. It says that the acceleration of an object is directly related to the unbalanced force that's acting on it. So the harder that you're pushing on something, the more it's going to accelerate, is kind of what this is saying. We have a really simple equation that kind of sums up the second law that we like to use instead of saying all of this, and that is F equals ma, which you've probably heard before. The unbalanced force on an object is equal to the mass times its acceleration, and that acceleration is related, again, back to that unbalanced force. Let's take a look at an example of Newton's second law. Newton's third law is also kind of recognizable in terms of its wording. We've probably heard it before. Newton's third law states that every action has an equal and opposite reaction. And we in physics kind of hate the way that this is worded. We do not like using the word reaction. So we are not going to use that word. We are going to say that every action has an equal and opposite paired action. The reason why we don't like to say reaction is because it implies that it happens afterwards. However, the action and reaction are simultaneous. So we like to instead think about how every action has an equal and opposite paired action. So that third law we like to call, instead of this action-reaction business, we like to say that forces come in pairs. So you right now are sitting on a chair, but that chair is also pushing up on you. You're pushing down on the chair is pushing up on you. That's a paired force. It's not happening one after the other, it's happening at the same time. So let's see an example of Newton's third law. I'm standing on this table right now, and I'm going to jump off onto the ground. When I do that, when I'm in the air, the only force that will be acting on me will be the force of gravity, pulling me back down to the earth. But remember, for every action, there's an equal and opposite action. So I will be pulling on the earth just as much as the earth is pulling on me. Why doesn't the earth move? Well, because the earth is a heck of a lot more massive than I am. The earth pulls on me, and it looks like I am moving down to the earth because I'm a lot less massive than the earth. But technically, I'm also pulling the earth up to meet my feet. And that's Newton's third law. Forces come in pairs. And those are Newton's laws. That's all for this episode of Physics in Action. I hope you enjoyed learning a little bit about Newton's laws and our 5 fabulous forces in physics, and hopefully you will start to see them in your daily life. Thanks for joining us once more on Physics in Action. I am your host, Miss Nielsen, signing off.